Section 5.4 is something called logarithmic functions. Do you remember how in section 5.3 we said that exponential functions have inverses? Well, logs happen to be the inverses of exponential functions. The logarithm with a base a of a positive number x, denoted log base a of x, is defined by log base a of x equals k if and only if x equals a to the k. What we see in this definition of a logarithmic function is a way that we can rewrite a logarithmic equation as an exponential equation. What I want you to notice here is that the base of the log is the same as the base of the exponent. So the base of the log is the same as the base of the exponent. Also notice that the log is equal to what is in the exponent. Notice that this log base a of x is equal to k, and when I rewrite that log as an equivalent exponent, k is the exponent, and that's what log was equal to. This part of the log is called the argument, and notice the argument stands alone whenever you rewrite the log as an equivalent exponential expression. The way I remember this is I don't like to be around people that argue, so the argument of the log stands alone when I rewrite it as an exponent. Notice the rules that we had for the base of an exponential expression are the same as they are for the log. A log of base a has to have a be non-negative and not equal to 1, and the base of the log is the base of the exponent. So this results in an exponential function log base a of x. This is called a common logarithmic function with base a. We do have inverse properties of logs. Remember I said that logs are inverses of exponents. So if we take an exponent of base a and we put it inside a log of base a, we're going to get out what we put in. Remember when we discussed inverse operations or inverse functions, we said that f composed with f inverse of x is equal to x. When you compose a function with its inverse, you get out what you put in. So here I've got a log base a that's an inverse of an exponent base a, so I get out what I put in. Likewise, if I put a log base a into the exponent of a, I get out what I put in. In example 1, we're asked to simplify each log by hand. In order to help us do that, I'm going to rewrite the arguments of these logs. I could rewrite log base 3 of 81 as log base 3 of 3 to the 4th power because 3 to the 4th is 81. Notice now the base of the log and the base of the exponent are the same, so that means that these will cancel each other out and this will be equal to 4. On part B, I could rewrite this as log base 4 of 1 over 4 to the 3rd power, because 64 is 4 to the 3rd power. Well, that is in the denominator, it's not in the numerator where it needs to be in order to have 4 raised to a power. So I can use negative exponents to help me rewrite this as log base 4 of 4 raised to the negative 3, because to make a negative exponent positive, I would just flip this into the denominator, and that exponent's positive in the denominator. So when it moves up to the numerator, I have to make that exponent negative. Now the base of the log and the base of the exponent are the same, and this would be equal to negative 3. On part C, I could rewrite this as log base 4 of 4 squared. Because the base of the log is the same as the base of the exponent, and 4 squared is 16, I would say that this is equal to 2. On part D, we have something new, this ln. If you look at your calculator, right here above the ln, you see that e to the x, and that's how we got our natural exponent, Euler's number. E's and ln's are inverses of each other. What that means is I could rewrite the natural log of e raised to the 0.67 as log base e of e to the 0.67, and that's going to give us 0.67. I could actually verify this one on my calculator by taking the natural log of e raised to the 0.67, and that's going to give me 0.67. This just reaffirms that a natural log is a log base e. Now a common log, we said, is a log base 10. The common logarithm of a positive number x is the exponent k such that 10 to the k equals x. So our input x is equal to 10 to the k. That's log of 10 to the k. The output then would be k. We would say log base 10 of x equals y if and only if 10 to the y is equal to x. This is taking this common log function and rewriting it as an exponent. By rewriting this as an exponent, it's easier to see how to get points to graph this function. So here I have 10 raised to the negative 1. If my exponent is negative 1, I get 10 raised to the negative 1, which is 1/10. What that means on my graph is when y is equal to negative 1, x is 1/10, which is really close to the x-axis. If I plug in a 0 in place of y, that gives me 10 to the 0. 10 to the 0 is 1, so I have a point here at 1, 0 on the graph of the logarithm function. If I plug in a 1 in place of y for my exponent on my graph of log x, I end up with 10 to the 1 is 10. So I would have the point at 10, 1. That's how I get these points that I use to graph a logarithmic function. Notice on the common log function, the domain goes from 0 to infinity. The range is all real numbers because these are going to the right, but they're also slightly increasing. And down here, our y values, our range values are decreasing. So the graph is continuous and increasing, and the graph passes a horizontal line test, which means that it's 1 to 1. The y-axis is a vertical asymptote. Remember how I said logs and exponents are inverses of each other? And how we get an inverse function from a function is we swap the domain and the range. This graph of y equals log base 10 of x could be rewritten as 10 to the y equals x. If I switch x and y, I end up with y equals 10 to the x. This is an exponential function, whereas this one is logarithmic. On the logarithmic function, the domain goes from 0 to infinity. On the exponential function, we said the domain is all real numbers, and the range goes from 0 to infinity. Well, notice when I switch x and y, I end up swapping the domains and the ranges. On our exponential functions, we said that we have a horizontal asymptote at the x-axis. Whereas with a logarithm, we switch the x and y, the y-axis becomes a vertical asymptote. This graph is also continuous, positive, and increasing because the base is bigger than 1. And this graph has a y-intercept at 0, 1, whereas this graph has an x-intercept at 1, 0. Notice we're just switching x's and y's and all of the properties associated with x and y's when we switch from a logarithmic to an exponential function. F of x equals log x without a base written is called the common log function. So if you ever see a log written without the base, assume that it's a log base 10. This is the log button that you have on your calculator. It's a common log button. The ln button is what we call a natural log button. In example 2, we're asked to simplify each logarithm by hand. Well, I could use the inverse properties and rewrite this as log base 10 of 10,000, and 10,000 is 10 to the 4th power. Therefore, this would be equal to 4. On part B, I could rewrite this as log base 10 of 7 to the 0. Well, 7 to the 0 is equal to 1, because anything raised to a power of 0 is 1. I could rewrite that as log base 10 of 10 to the 0, because 10 to the 0 is also 1, and that means that this would be equal to 0. On part C, I could rewrite this as log base 10 of 10 raised to the negative 1, because a power of negative 1 is the same thing as 1 over 10 to the positive 1, and that means that this will be equal to negative 1. On part D, I could rewrite this common log as log base 10 of 10 squared raised to the 1/3 power. 100 is 10 squared, and remember the cube root is the same thing as raising this to the 1/3 power. Well, when we raise a power to a power, we multiply the exponents, and that means that this will be equal to 2/3, because 2 times a third is 2/3. On part E, we notice that 0 is not in the domain of the logarithmic function, and if you've forgotten that, we can look up here and see that the domain does not include 0 because it uses a parenthesis instead of a bracket, and therefore this would be undefined. Log of 0 is undefined. Now, if you recall when we first discussed inverse functions, we said that the graph of a function and its inverse are symmetric about the line y equals x. That's true with all inverse functions. So here's a graph of y equals 10 to the x and the graph of y equals log base 10 of x, the common log function. Notice if I were to fold this graph in half along this dotted line, the red graph and the blue graph would match up perfectly. So looking at the graphs of the exponential and the logarithmic function, there's a couple of things that I want to point out. On an exponential function, the domain is all real numbers. It goes from negative infinity to infinity, and the range goes from 0 to infinity. But on the logarithmic functions, here the domain goes from 0 to infinity, and the range goes from negative infinity to infinity. On the exponential function, we have an y-intercept at the point 0, 1, but on the logarithmic function, we have an x-intercept at the point 1, 0. Notice we switch x's and y's and we switch domains and ranges. On the exponential function, we have a horizontal asymptote at y equals 0, the equation for the x-axis, and on the logarithmic function, we have a vertical asymptote at x equals 0, the equation for the y-axis. Because these functions are inverses, we end up switching x and y's, and that causes these properties to fall out. Notice on this graph, both of these functions are increasing, and that's because the base is bigger than 1. If the base of the log is bigger than 1, or if the base of the exponent is bigger than 1, then the function is increasing. If the base of the log and the exponent are between 0 and 1, then the function will be decreasing. So the following inverse properties hold for the common log. Log of 10 to the x will be equal to x, and 10 raised to the log x will be equal to x. That's because there's an assumed base of 10 on this log. Just like when we had square roots and cube roots, if I had the square root symbol with no number here, we assumed that that index was 2, but if I had a 3 there, we knew that that was a cube root. If there's no base on the log, we assume that it's a log base 10. Now, if we have a base 2 logarithmic function, we're going to plug in some numbers for x and solve for y, or plug in y's and solve for x, and it generates this graph of y equals log base 2 of x. What I've done here is I've graphed the function y equals 2 to the x alongside the function. This is a graph of y equals log base 2 of x. And you see symmetry about the line y equals x. And all of the previous properties still hold. If we have a base e for a log or a natural log, you can see that y is equal to the natural log of x. If I plug in numbers for x, then use the calculator to evaluate natural log of x, this is what we would get. In red here I have a graph of y equals e to the x. In blue I have a graph of y equals the natural log of x. And in green I have the graph of the linear equation y equals x. Notice the exponential and the logarithmic functions are symmetric about this line y equals x. Now there's two special logs that we talk about, and those are the ones that have buttons on the calculator. That would be the common log and the natural log. The common log means that we have a log base 10 of x, but what we write is the log without any base. A natural log means we have a log base e of x, but we don't write log base e, we write natural log x or ln x. And these are two buttons that we have on our calculators. In example 3, we're asked to use inverse properties to evaluate each of the expressions. Notice here the base of the log is the same as the base of the exponent. Those are inverse functions of each other, so we're left with just the pi. Here I have 9 raised to the log base 9 of 4x. The 9 for the base and the exponent and the 9 for the base and the log are the same. These are going to cancel each other out, and we're just left with 4x. Once again, here the base of the log is the same as the base of the exponent that's in my argument, so this would just be equal to 4.6. And here's a prettier picture that shows you the graph of y equals 2 to the x with the inverse function y equals log base 2 of x. Here's a graph of y equals e to the x, y equals the natural log of x is the inverse. Notice both of these functions are increasing. Actually, all four of these functions are increasing because the bases are bigger than 1. Remember, e is about 2.71828. In example 4, we're asked to solve this equation. Whenever you're asked to solve an exponential equation, the first thing you want to do is isolate the exponent, and I can isolate the exponent by dividing both sides by 4. When I do that, that's going to give me 10 raised to the 3x equals 61. Because the base here is equal to 10, I can rewrite this equation as a common log. Remember, on the common log, the base of the exponent is the same as the base of the log, so I have 10 as my base. The argument of the log is what stands by itself because the argument stands alone, and what the log is equal to is the exponent. So that's how I would rewrite this exponential equation as an equivalent logarithmic equation. Next, I want to isolate the variable by dividing both sides by 3. And when I do that, that gives me x is equal to log 61 divided by 3. I don't need to write the base of 10 here. Now I can use my calculator to get a decimal approximation for this. So on my calculator, I'm going to get log 61, close the parentheses for the argument, and then divide that by 3. Rounding this to 4 decimal places, then I get 0.5951. If I ask you for the exact answer, this is the one that I want. If I ask for a decimal approximation, this is the answer that I want. In example 5, we're asked to solve another logarithmic equation. On this one, I want to get the log by itself, so I'm going to do that by dividing both sides by 5. What you do to one side, you have to do to the other. And that's going to give us log of 2x equals 16/5. I don't know what this is when it's written as a log, so let's try rewriting it as an exponent. So I used the definition of logs, y equals log base a of x if and only if a to the y equals x, to rewrite this logarithmic equation as an equivalent exponential equation. So the base of the log will be the base of my exponent. The base of the log, remember, if it's not written, is going to be 10. The log is equal to the exponents, so that's 10 raised to the 16/5 equals, and then the argument of the log stands alone. I can solve this equation for x by dividing both sides of the equation by 2, and when I do that, I end up with 10 raised to the 16/5 divided by 2 as my final answer. This would be the exact answer, but I could use my calculator to get a decimal approximation. So on my calculator, I would take 10 raised to a power of, open parentheses, 16 divided by 5, close the parentheses, then move my cursor back down out of the exponent, and then I would divide this whole thing by 2. So 10 raised to the 16/5 divided by 2 is 792.45 if we were rounding to do decimal places. So remember, this is a decimal approximation, this is the exact answer. In example 6, we're asked to solve each of the following equations. So let's go through this same process and see if we've learned anything. So I start with e to the x equals 5. Now remember, natural logs and e's are inverses of each other, and a log is a mathematical operation. So if I perform the same mathematical operation to both sides of the equation, I should maintain equality. So I'm going to take the natural log of the left-hand side of the equation and set that equal to the natural log of the right-hand side of the equation. ln's and e's cancel each other out because this is a log base e of e raised to an x, and that gives us x on the left-hand side, and that's going to be equal to the natural log of 5. I can use my calculator then to get a decimal approximation for this. If I wanted a decimal approximation, natural log 5 would be the exact value though, but natural log 5 is approximately equal to 1.609. So my exact answer is the natural log of 5. My approximate answer is 1.609. On part B, the first thing I want to do is isolate this exponential expression. That means that I need to add 7 to both sides of the equation. And when I do that, that gives me 3 times 2 to the x equals 27. Then I can divide both sides by 3. Remember, what you do to one side, you have to do to the other, and that gives me 2 to the x equals 27 divided by 3 is 9. Now I don't know what this is exactly because I can't rewrite 9 as a power of 2, but what I could do is rewrite this exponent as a log. The equivalent log would be a log base 2 because the base of the log is the same as the base of the exponent. The argument of the log is what stands by itself when it's an exponent, and then whatever the log is equal to is the exponent, so that means that this would be equal to x. So my exact answer is going to be log base 2 of 9. Is it possible to get a decimal approximation for this though? Well, I'm pretty sure we can't do it without the calculator, but when I look at my calculator, I don't see a log base 2 button here. Well, in order to use your calculator, we use something that's called a change of base formula. The change of base formula basically says that if you have a log base a of x, you could rewrite that as the natural log of x divided by the natural log of a, or the common log of x divided by the common log of a. So on my calculator, if I want to get a decimal approximation for log base 2 of 9, what I would look at is the natural log of 9 divided by the natural log of 2. Or I could even do the common log of 9 divided by the common log of 2. Notice I get 3.17 both times. So this would be my approximate answer that I found using the change of base formula. But this is my exact answer if I ask you for the exact answer. And this wraps up section 5.4.